Hello everybody, my name is Alessia Ritacco and I work at the LPC Institute in Grenoble. It's a pleasure for me to present the COSMOCal project on behalf of the collaboration, including all the different institutes that are listed on the bottom of this slide. Before going into the detail of the COSMOCal project and the proof of concept and the proposal for space, I will briefly introduce the scientific motivation and the state of art that inspired this project. So the main goal that is inspired our project is concerning the probing of the inflation theory. Nowadays, the cosmological community is targeting the detection of the B modes, the pattern of B modes in the CMB polarization that enclose the imprint of primordial gravitational waves produced during the inflation epoch. But this B mode patterns is very faint with respect to the temperature and the E modes, as you all know. And the two different patterns, the E mode and the B modes, are distinguished by an angle. So if we have any miscalibration from our instrument, we will confuse the two signals. So we need to improve our instrumentation in terms of sensitivity, systematics effect control, calibration accuracy, and foregrounds subtraction of dust and synchrotron emissions. Another science case of very high interest today is the physical effect called the cosmic birefringence that will naturally convert the E mode into B modes. And these two different patterns are distinguished by a cosmic birefringence angle, in this case, the beta angle. And of course, if we have a miscalibration coming from the instruments, we will not be able to distinguish the physical effect from the instrumental effect. So improving the angular accuracy in our instrumentation, which is the target of this talk, will break the degeneracy between the birefringence angle and CMB detector's orientation, allowing us to explore a physics that is beyond the standard model and giving insights into the fundamental particles, nature of their matters, and also primordial magnetic fields. In some cosmic birefringence are coming from Planck data, but however, recent results from Diego Palazuelos et al. Also showed that the possible correlation between E and B coming from the foreground dust emission could bias the detection of the cosmic birefringence angle. This has been confirmed also in our studies shown on right, summarized in this slide, where we say basically that current foreground models are lacking of information to take into account all the polarization seen that is describing our sky. So this is most likely due to a EB decorrelation with frequency due to the variation of the polarization angle along the line of sight, due to a coupling between dust physics and magnetic fields. So in order to improve the dust emission measurements for foreground subtraction, we are also to improve our absolute angle calibration to be able to detect this tiny difference and variation of the polarization angle along the line of sight. So the reconstruction of the dust emission has a major impact on galactic astrophysics and also on foregrounds models for CMB detection. Planck polarization data allowed us to have a unique perspective that interfaced with ground-based experiments, give us a hint on the interplay between dust and magnetic fields. However, we are constrained today by the precision of our measurements, and so the project that I'm going to present will also give an insight into the physics playing at the dust emission of the galactic regions. So a sky reference on the sky that is commonly used and the most reliable on the Maghreb sky is the Crab Nebula Orta wave. Here I show very briefly the three maps observed on SOXI, Q, and U by the NICA instrument that allowed to go into detail by taking also other observation available and reconstructing the spectral energy distribution of the source. This is one fundamental part of candidating sky references as a calibrator, because we need to know the physics inside the source to be able to know if it can be stable in a large range of frequency. Of course, our study was targeting the polarization angle, so this compendium of different observations allowed us to extrapolate the total weighted polarization angle with uncertainty of obtained of 4.27. However, these are affected by systematics that are related to different experiments. If we only take the statistical uncertainty and we extrapolate the bias on the beam modes Pago spectrum that we have access if we use the Crab Nebula and these measurements as reference, we see that we are completely blind on a part of the sky where we expect the beam mode signal. So we need to improve our absolute calibration that is concerning the total experiments in terms of beam characterization, removal of the leakage between E and 2 polarization, the detector scores polarization, and also all the absolute calibrations. So these are the reasons that inspired us to go into this, to propose this COSMOCal project that is meant to have a reference very well characterized in the sky, so an artificial calibration source placed in geostationary orbit that will be visible from different large aperture telescopes on Earth that would be, in this case, very well calibrated as the Simons Observatory Large Aperture Telescope, the IRAM Altimeter Telescope, and SRT to cover the large band of focus for our project, and then use those telescopes to observe sky references as the Crab Nebula and deliver polarization maps of astrophysical sources very well characterized in terms of physics and the large band, and to offer these polarization maps as reference for the physics, for ground maps, and also for CMB telescopes. So the COSMOCal project started in 2022 as it has been funded so far by Census, CNES, and the École Normale Supérieure of Paris, and we started developing a prototype to be tested with the NICA 2 instrument at the IRAM Altimeter Telescope. In 2023 and 2024, we tested all the different components of this prototype, and we finally this year fully tested the prototype in the lab first and at the telescope after just 1 month ago. Now we are proposing to develop a space prototype, and we are waiting for the answer of the scientific committee decision about these 2 years of fundings to be ready for the hosted launch by the Eutelsat Telecom company that is expected in 2029. The COSMOCal prototype consists of a part that is the microwave source, and this emitted source, this emitted microwave signal goes into through the wire grid polarizer, ensuring 100% of polarization, and then we have an optical laser illuminating this wire grid to produce a diffraction pattern that is shown on the image on left. And through the data analysis of the different images of the diffraction pattern, we can ensure an independent measurement of the polarization angle of output of our instrument. And the optical system will also include a flip mirror that is allowing us to image also ground references and to recover the exact position of the prototype with respect to the telescope. This prototype has been conceived for a test on Earth in front of the IRAM 30-meter telescope. That is why we need ground-based references. The results of the laboratory test showed promising results beyond the goal that was 0.1 degree on the uncertainty of the polarization angle. All these results are summarized in a forthcoming paper. So this laboratory test also consisted in checking the response of the detectors mounted inside a cryostat. We have used the cryostat, which has the same technology and the same detectors that are mounted on the NICA 2 instrument. It is available at the IRAM 30-meter telescope, and we use a different polarizer to check the variation of the polarization in the path between the COSMOCal prototype and the detectors. We have established a model that is based on an optical model, and we observe actually this variation when we turn, when we rotate the polarizer. And on the left, it summarizes the three different situations where we can see the detectors data point in yellow and different fits that we have tried to put in place. Counting also sometimes for parasitic components, as we were understanding that in the room that was not appropriate for this kind of measurement, was not isolated, the instruments, there have been reflection that have caused the parasitic signal. However, even if on the detector sides, these are limitations for our measurements, independently, the COSMOCal and the receiver data analysis produces an independent measurement of the polarization angle within 1 to 3% in absolute value. So these were promising results that inspired us to ask for an observing campaign at the IRAM 30-meter telescope, and our idea was to put the prototype, the COSMOCal instrument, in front of the large antenna of the IRAM 30-meter telescope as to be seen by the NICA 2 instrument. So it was placed on the top of the mountain in front of it. The idea was to test the photogrammetry, so the reconstruction of the position of the prototype with respect to the antenna, the response of the camera, the NICA 2 camera, studying the instrumental effect at the interface between the large antenna and the COSMOCal, and also checking the consistency between COSMOCal polarization angle and NICA 2 instrument ones. So first of all, as I said, the photogrammetry is very important to determine the roll angle between the COSMOCal box and the coordinates of the IRAM 30-meter telescope that will add an uncertainty to our polarization angle reconstruction. So we have placed different ground references that are seen by the CCD camera, by this optical telescope that is mounted inside the COSMOCal instrument. On this side, the data analysis is ongoing to improve the reconstruction and the recognition of the position of the instrument with respect to the antenna. The response of the NICA 2 detectors has also been our baseline to start the data analysis. And here you see time order data showing the different signal coming from the chopper that we have mounted to have a baseline to subtract the background coming from the antenna. And you see the chop up and down, and also the modulation produced by a continuously rotating upward plate, which is the baseline of observation in polarization for NICA 2. On the right, you see the power spectrum of this time order data, and you see that you can distinguish the different harmonics produced by the chopper and also the upward plate. On right, sorry, it is highlighted where we observe the polarization of the signal. So all the data analysis is based on distinguishing the chopper signal to the from the upward plate polarization signal in order to reconstruct the polarization itself. Another point was the misalignment of the COSMOCal source. To perform this, we have to be sure that we were aligned. We have first performed optical simulation. We have seen that very tiny misalignments will produce a different primary mirror illumination. So at the telescope, we have tracked different position in azimuth and elevation. This is the amplitude of the signal in polarization intensity. I have missed the value hertz, so for the signal, and we have maximized the signal, establishing what was the perfect offset in azimuth and elevation with respect to our original position of the COSMOCal source. So once we have done this, we have turned the polarizer inside the COSMOCal box to see if we could recognize the differences and the correspondence with the NICA 2 camera, polarization angle reconstruction, and as you see by this plot showing the preliminary analysis, we have a perfect correspondence between the two different data analysis on the NICA 2 angle and the COSMOCal angle. Of course, to establish the uncertainty and take into account all the different instrumental effects, we need to investigate with major details the response of all the detectors as distributed on the focal plane and estimate the associated uncertainty. So, concerning the space proposal, as I said at the beginning, we have established a partnership, a cooperation for the new space with a telecom private company, which is called Eutelsat. So the idea is to use the platform that will be launched in 2029, and they will launch our payload in geostationary orbit to be seen from Europe and Atacama. So the payload design is coordinated with the expert engineer from the Eutelsat group, and this allowed us to establish the specification to be included in the Eutelsat call for tender to be issued next year in 2025. The space payload includes 3 different frequencies, so it's a multi-frequency source and an optical system, a microwave telescope that will be able to focus different telescope at a time. So just to orient our source of emission in the different place and area of the Earth. The challenges in this sense are the optical design, the thermomechanical design, and the interface-based platform. The electronic chain is also a bit complicated, but is based on the design that has also been used for space experiments, JUICE. And here the challenges will be to include different frequencies, so having a multi-frequency electronic chain which occupy a very small space in the box in our payload, and then having a high signal power to be seen by the Earth and the signal stability. To get into the conclusion, this space proposal has passed the first selection, so we are waiting for the final decision of the scientific committee. But in general, this COSMOCal project is showing a timely contribution to paramount goals on observational cosmology faced with the deployment of ambitious CMB experiments. It has itself the ambition of relying different datasets at small and large angular scale to give a deeper perspective on the CMB data analysis, but also on the dust polarization analysis and the physics of the interstellar medium. This project offers training opportunity for students in space instrumentation, microtechnology, astrophysics, and cosmology. And the space proposal has been supported by proof of concept that has been successfully tested with the NICA 2 at IRAM 30-meter telescope, and the preliminary analysis is showing promising results. So the cooperation between private and public entities has been chosen to minimize the proliferation of spacecraft in orbit around the Earth. Hopefully, it was of interest for you, and I thank you for your attention.